So we've got a bit of an application question here about a casino that's playing a particular card game. What I'd like you to do is pause the video right now and read the question. Okay, so we know now we've got a card game. It's worth keeping in mind there are 52 cards in a deck. There are 4 suits, which means there are 13 cards in each suit. And we need to have a look at what our financial situation is for this casino. So let's start off by making a probability distribution table. So what I've done is I've set up a table here that has each of the cards that a dealer could turn over. And now what I'm going to do is I'm going to talk about the payout. So if the dealer turns over a 2, then the payout is -$6, which means the dealer keeps the $6 which the player paid to play. 3, 4, and 5, and 6 are all the same. It might be helpful if I put these lines in as well. So I'll do that. Look at that, they're done. Magic. Now, if there's a 7, then the dealer will give the player $1. Okay? So because the $7 minus the 6. So $1 would be the payout. 8 would be $2, 9, 3, 10, 4, Jack 4, Queen 4, and King 4, because they're all, according to the rules, a payout of $4, $10 payout, so 10 minus the 6 is 4, and the ace is $11, so it's a $5 payout after the $6 entry fee. Now what I'm going to do is I'm going to work out what the probability of each particular card is. Now, we know that each card is equally likely. So each probability will be 1 in 13, and I'm going to fill all those out as well. So to work out the expected payout, which is, that's the mean or EX, what I will do is I'll multiply the -6 payout by the probability. So there's 5 of them, so it'll be 5 lots of -6 times 1 over 13, plus there's 1 lot of 113 with a $1 payout, plus $2 payout, and the chance of that is 13, plus a $3 payout, and the chance of that is 1 on 13, and so on. There's 4 lots of $4 payout, so that'll be that, and we add the 1 lot of $5 payout, and the chance of that is 1 on 13. And if I do all that in my head really, really quickly, I get -0.2308. So what that means is the average payout per game is 0.2308. So the casino actually wins by 23 cents per game to the casino. So this looks like it's a good game as far as the casino is concerned. Now the next part of the question asks about 1,000 games being played and how much money would the casino expect to make if they charge that $6. Now we remember that in part A, the expected profit per game for the casino turned out to be if I go to some more decimal places, 0.23076, and actually 69 per game, so that's in dollars. So therefore, for 1,000 games, the profit equals 1,000 times 0.230769, which comes out to $230.77. So that would be expected profit for 1,000 games. But wait, there's more. The next part of the question asks us, if we redefine our payout as the amount of money the casino gives the player, then it's asked us to complete the table. So remember, the dealer pays nothing for a 2, 3, 4, 5 or 6. And then for these values, it'll give 7, 8, 9, 10, 10, 10, 10 and $11 respectively. The chances are still the same, 1 in 13 for each of them, so we can fill all of those out as well. So there's our table filled out with all our 1/13s. Now, the next question is going to be the amount of money the dealer will pay a player at the end of each game. So this will now be the expected value of D. And we'll do this exactly the same way. So there are 5 times 0, 5 chances of 0, plus there's one chance that $7 will be paid, so that's a 1 in 13. For $8, it's 1 in 13. For $9, it's 1 in 13. For $10, there are 4 of them, so it's going to be 4 times $10 payout and a chance of 1 in 13. And for $11, there is one chance of an $11 payout, and that's 1 in 13. And if I do a quick mental calculation for that and add all that up, I get 5.76923, approximately. So this is the amount of money that the dealer would expect to pay out per game. That's not considering the $6 fee. That's just saying every game the dealer would expect to pay $5 out to somebody. Now we're asked if this figure makes sense in the context of Part A. And Part A said, remember, that there was a 23-cent profit or thereabouts per game. So I'm comparing a 23-cent profit per game to this average payout of $5.77. Now, if I pay $6 and there's an average payout of $5.77, then the difference is 23 cents. So that is in line with my assumed 23-cent profit per game. The next part of my question asks what the entry fee should be if the game was going to be fair, which means how much should we charge someone if the casino doesn't expect to make any money? Ridiculous concept, I know. But still, what we would need to charge is our expected value. So the answer to this would be $5.77, which is our expected value. And finally, we're asked, if the casino decided to make $20 the payout for an ace, how much in whole dollars would the casino need to charge to ensure a win for them? What's the minimum amount? So what we'd need to do is we'd need to say, okay, our expected values, remember, when we go back to the table that we did in Part C, we'd have 5 times 0 times 1 on 13 plus 7 times 1 on 13 plus 8 times 1 on 13 and so on. But remember, we have 4 lots of $10 payouts, and now our ace is 1 lot of a $20 payout for 1 on 13, and that comes to $6. It'll be 6.4615. So the lowest whole dollar fee that would expect in a win for the casino would be $7 per game, and the casino should win given those new payouts for aces.